Second. Okay, yeah, it's fine. All right. So and then after we have one robot, well, we're supposed to use some platform or a computer to control this robot. So I'm going to introduce Robot Braki. It's a website platform to control robots. And we will do some exercise, show you some demos first and do some exercise related to Robot Braki to show you how we control robots. And in the next hour, I will show you my previous research for my PhD degree about multi-robot systems. Well, now we just one robot, right? Like soft robot or LinkBot here is only one robot. But how we control many robots at the same time, this is a key point. So in the next hour, I would like to introduce how we control multiple robots with many computers and with a certain method. And at the end, probably we can think of how we use many software robots to deal with your project for this course. Okay, so let's watch some videos first. And inside these videos, they will tell you some key features in the robot. Can they hear any sounds? Okay, it seems good. Yeah, just the voice, the sound. Oh, this one. Okay, I found it.
Wow, what is that thing flying on the ground? Hello, now 75. Hello, now 41. Oh, I don't know. I am sorry. I suppose I should get up. That's better.
Okay, let me stop here. So here at the beginning, well, we may see that in order to design this humanoid robot, first of all, we need some parts like arms, legs, body, of course, and head, right? These are mechanism parts. But how about the movement parts? Well, you can see there are many joints for the knees, toes, fingers, arms, or heads. There are many joints on this robot. So how do we control these joints? Well, we need motors, right? DC motors. So we call it actuators. Well, I will show you the slides later. And then inside the videos, we may probably see some sensors, right? No matter the touch sensors. I remember there's a pressure sensors on the feet, right? And the voice sensors or sound sensors. So in order to receive some feedback around the surrounding, we need some sensors on the robot. And in order to react the environment, we have some cameras, right, to detect the object. Cameras to detect objects. So although this is a very advanced robot, well, compared to this software robots, well, if we add some sensors on the software robots, or if we add some cameras on it, well, we may create an advanced robot instead of just a single tiny software robot there. So these are some key features in order to create a humanoid robot with sensors, cameras, and motors, and probably like speakers, so that it can speak with humans. All right, let me show you another video. This one is cute. It's very advanced one. I really like to watch videos from this one, Boston Dynamics. Probably some of you watched these videos before because the robots from here are very famous. Start. Okay.
Atlas is the culmination of over a decade of hydraulic humanoid robotics work at Boston Dynamics. Atlas stands about 5 feet tall and it's about 190 pounds. It's battery powered and hydraulically actuated 20 freedom. It has RGB cameras and depth sensors, which provide input to its control system, and all of the computation required for control, perception, and estimation happens on board the slate computers. At a practical level, it's a platform for us to do R&D on. And as an Atlas team, we're encouraged to push, that platform to its limits, like do the most crazy, exciting, high power stuff we can do with it. And so we're always expanding and pushing the limits of Atlas capabilities. And then, hopefully by extension, extending the capabilities of the company as well at the same time. Our core is a useful organizing activity for our team because it highlights several challenges that we believe to be important. First, how do we build a high power density mobile robot that's capable of extended athletic behavior? How do we design control algorithms that can create a variety of behaviors and control them robustly? And how do we connect perception to action in a way that both captures long-term goals like getting from point A to point B and short-term dynamic goals like adjusting footsteps and applying corrective forces to maintain balance?
What makes Parkour Mountain hard was not so much the individual moves. Those have been worked on a lot prior to kind of pulling together, but running the entire course, doing it in one contiguous set of operations really drives the need for reliability and repeatability. These are things that are pragmatic, but really difficult. And that's what the team really focused on. I think the biggest success is being able to show all of those exciting things pulled together and done repeatedly.
It can be frustrating sometimes. Robots crash a lot. It's not the robot just magically deciding to do parkour. It's kind of a choreographed routine, much like a skateboard video or a parkour video where it's an athlete that's practiced his moves dozens or hundreds of times even to get to that that high level, that exciting capability. So we're kind of doing the same thing here with Atlas. We're exploring how to push it to its limits, sometimes operating at those limits. And we learn a lot from that in terms of how to build robots that can survive falling on their face and getting back up and doing it again. We also learn a lot about the behavior, the control, the thing that puts one foot in front of the other. These videos are a true team effort. First, of course, we have the software team who is responsible for creating all the behaviors and control software required to execute the behaviors reliably on the robot. We have a hardware team who is responsible for making strategic upgrades to our robots that enable things like extended dance and parkour routines. Our technicians debug and repair a variety of issues that can range from broken mechanical parts to hydraulic leakages to electrical failures. And our operations staff is responsible for building these environments and repairing them when robots crash through them and helping us run the
many tests required to get this kind of demonstration to a high degree of reliability.
Hey, Tom, can I grab you a flathead?
Our job is to get it back out on the floor and working again. Sometimes it looks disastrous and like, oh, we've seen this before and we can fix it so easily. And then sometimes we end up with something that looks benign and it will take days to get down to a root cause and figure it out and then repair it. It's a balancing act between, getting down to root causes, improving designs, and keeping the robots running around out on the floor. Okay, nothing looks out of the ordinary.
The most rewarding thing about my job is that I never have to work very hard to explain why I love it. I love working on robots. I love working with people that have passion to push, to try new things, and really just explore things that have been unexplored. And I think almost every day at Boston Dynamics involves elements of that.
The work that we're doing now, I view as really just foundation building. We're building the core capabilities that we think any useful robot will need. And in doing so, we're really defining the next set of challenges that we're going to be working on over the next 2 to 5 years.
It's extremely hard, but it's also very rewarding. It's like I wouldn't want to be somewhere where I'm not working on like a super hard problem that nobody else is working on. So it's just that's the opportunity that we get to do here. 3, 2, 1.
All right. Well, this is the end of almost the end of a video, actually. Okay. Well, compare this robot with the previous robot. I believe this robot is much more advanced, right? You can see that it can do many very challenging motions, even we are not able to do, right? So how do we control this robot? How do we design the system or control system to make it jump? What else? Get from the floor or the backward jump, something like that. It's very difficult. So it's usually we use some machine learning methods to help it control or help it to do these fantastic motions. So in the part of the video part, you can see that, I don't know where is it. Or you may see that some human beings do almost the same motion at the beginning, right, at the first, and then collect this data and put it on this robot. So this robot may learn from humans and then do these challenging motions. So besides some sensors, cameras, well, in this video, it also shows that it has several sensors, cameras, and also very complicated algorithm to help it jump and do other challenging motions. So let's go back to my slides. Let's give a little summary related to these 2 videos. First of all, of course, we need a mechanism, basic mechanism to create humanoid robots. Then we need several sensors, no matter range sensors like LiDAR or sonar sensors to measure the surrounding. And what else? Force sensors, touch sensors, or accelerometers, gyroscopes. Well, these are all sensors in order to get enough information around the environment. And then we need the control system with several controllers like Arduinos and computers like Raspberry Pis or much more advanced computers or even laptops, of course. And what else? After that, we're supposed to react to the environment. So usually we call them actuators like speakers, motors, or LEDs, right? So we can probably see or show as the eyes. These are some key features in order to create advanced robots? Well, I believe it's very difficult to design the motion like a previous advanced one. Well, because the program is very, very complicated. And of course, the mechanism is also complicated. So we need a middleware. It's a technical term to represent that how we control these devices or how we communicate with these devices. As I mentioned before, we may have several cameras, different cameras. They may be different. They can be the same, but usually there are different cameras, different sensors, or different actuators. So how do we connect these devices, correct, and how we control them? So in this case, we need a middleware. One of the very famous system called robot operating system. Usually we just call ROS. With this system, ROS, we may send signals or commands to these devices to ask the camera to take a picture or take a video, and also send the commands to sensors like ultrasonic sensors to receive the distance between the obstacles, and then send the information back to the computer. After that, this computer is supposed to make the decision, right? To make the correct motion in order to interact with the environment. Then it will control or send commands to DC motors to control them. This is a key feature we need in order to create a robot. I mean, the advanced robots, not a very simple robot. Questions? Okay, all right. Well, but if we just have that advanced robot, probably it's very difficult to understand how to control them, right? There are many, many joints with many devices like cameras or sensors. It's almost impossible to learn how to control them right away. So here, my previous advisor in the US created this one called LinkBot. This is an educational robot to teach elementary school, middle school, and high school students. So that's why it is very simple, but this is a robot. Let's see some key points. We have sensors right here, sensors, and we have motors. These are motors. We have two motors actually from this side and this side, another side. We have motors, sensors, and how about computers or controllers? Here, we use Arduino to control these motors. So we can receive some feedback from sensors and then use this controller to control these two motors or actuators. So yes, this is a robot, but it's a very simple robot. Then we may learn how to control it first. After that, we may control the very complicated humanoid robots in the future. Okay, here we may add some wheels. Well, as I mentioned before, we use this to teach middle and high school students to learn math, programming, and robotics. So we add some wheels for it as a very tiny vehicle here. Well, we can also put many link parts together to create like a robotic arm. So in this case, this is a little complicated compared to the previous simple one. We may have to control the joints on here and probably joints over here. So if we want to control this link bar to grab or grip the pen here like this, we need to control each joint, not only one single link bar. Each joint over here, there, and probably at the bottom. So here we need to write a little complicated program to control each joint in order to grab a pen. The last one is a recent project. Actually, I designed this actually. This is called the Magnum wheels. With these wheels, it can drive not just the forward, backwards. It can also drive to the left, to the right, directly, or drive diagonally. It's kind of an omnibot without any turns. although it still can turn. We will show you some examples later. As I mentioned before, although it is a very simple robot, we can still add some sensors like Arduino. Probably some of you are very familiar with Arduino and sensor, ultrasonic sensor. We may also add a computer, Raspberry Pi, to connect to the camera. So you can take a picture and recognize any object or obstacle in front of it, and then control this motion. So with this equipment, well, this ThinkBot can be an advanced robot. This is a very short demonstration about OmniBot and ThinkBot. Oh, there's no voice here. Well, as you can see, it can drive forward, backward. We control it with programs. We will show you later. It can drive laterally to the right and left. But of course, the tiny ThinkBot in the middle, it cannot. It can only drive forward, backwards, and turn. We will show you later. Here, it drives diagonally. Backwards, of course. I remember there's a turn. Come on, okay. Turn right, turn left. Almost done. And of course, after it turns, it can drive forward. We control it with several programs, but very simple programs, not complicated. You may play around it later on after we learn the robot broccoli platform. Okay, here, this is a platform. As I mentioned before, we need a platform called the middleware to control robots, right? Here, in order to teach young students, well, my previous advisor developed this website called RoboBrocky. With this website, we may control robots. Here is ThinkBots and OmniBots with these block functions. Instead of C programming or Python, well, sometimes students are not familiar with C or Python, or it's very difficult to learn how to write programs. But with block functions or block programming, well, for students, it's much easier to learn programming. So let me show you the website. Where is it? I remember about this one. Okay. If you have a computer, laptop, or smartphone, yeah, we can run it on smartphone actually. You may go to this website and play around. But of course, I will teach you how to use these block functions to control single ThinkBots and also the multi ThinkBots later. We may just drag these block functions to the workspace. Here, this is called a drive distance, which means we ask this robot to drive within a certain distance. Here it is in inches, but that's because we are in Taiwan now. Let me change to the metric system. Okay, it's supposed to change to C. Okay, centimeters now. So this ThinkBot is supposed to drive 5 centimeters in this case. After we drag this block function, we may click run. And it will run, just drive 5 centimeters. And if we ask it to turn left or turn right, here 90 degrees or 45 degrees, anyway. Press run again. So you will drive 5 centimeters and then turn left 90 degrees. So in this case, well, it's very simple to write a program to control a single ThinkBot in this software or in this platform, right? It's not very complicated. So here we may write a very long program, something like that. Yeah, right. Turn left, right, turn left, right. Okay. A little longer program. So where should we go? Now it's at the origin. So if we drive 5 centimeters, turn left, let's maybe add one more drive distance here. So it's supposed to drive 10, 5, that coordinate, right? So this is how young students learn programming, math, and robotics here with this platform. Well, don't estimate this. Although it looks like stupid, but please don't underestimate it. We can see or write C programs here. If you are familiar with the C program, well, I believe you might understand how it means, such as include the header file, add a class or library, define some variables, and then use several functions to control this robot. This is let me check my slides here. Okay, this is a very simple demonstration that how we teach students how we control this tiny robot to the bakery shop and then go to a gas station, something like that. But for you guys, you are graduate students, right? Sorry, undergraduate students. Well, let's think of that how we control this robot to get the location we want within the specific time. Such as right now it's over here around 3, 2 coordinate. Then we want to go to the company within probably 20 seconds. How do we do that? So we need to set up the speed, correct speed, right? And then drive the correct distance and of course the turns. And then we may make this robot drive to the company within the specific time as we want. Let's see here. In the background here, setting backgrounds, we may choose the background we want, for example, like this. So you will change to the background we want. And then if we are unable to see the robot, this is too tiny, okay, medium. You can add the robots. And then we may adjust its initial position via this way. Okay, let's do 3, 2, okay. Then as I mentioned before, probably we need to exit to drive to a company. What's the coordinate is? 30, 18, okay. So let's see. Probably this is 7, 4. And turn left and drive. Oh, I want to keep this Lingbot on the road instead of just crossing these buildings. I want to keep it on the road and drive to the company within 20 seconds. So in this case, we need a setup speed here. Why is it in inches? I didn't remember I set up to metrics. Down. Okay. Centimeters. Okay, well, we have to set up the correct distance in order to make it possible. 13, I guess. I think this is enough. Where's my robot? Okay, here. And then click run. Oops, I calculated wrong. All right, never mind. It runs weird for now. All right, so it's obvious that for my last block function, the value is incorrect now because it just drive on the way. We probably need more 10-ish, probably 13 centimeters to make it to the company. And you may see the running time over here is about 9 seconds. So probably 4 centimeters per second, this speed might be enough. Well, you may play around with it now, probably 5 minutes. It's very simple. You may also try some other functions like drive time. It will just drive 4 seconds. 4 seconds and drive to 16 centimeters, something like that. I guess there's a bug here now. All right. All right, never mind. I guess there's a bug here. Probably we can only use the inches, I guess. Let's play around with it for 5 minutes, and then I will go through the Omnibot later. Oh, by the way, I mentioned that we're supposed to use a controller to control robots, right? Here, we may also use Arduino here. If you used the Arduino before, you may probably familiar with some functions, pin mode, digital write, digital read, analog write, analog read, and so on and so forth. Well, we can control Arduino here with this website. Actually, we can click the link button on the top left corner, and then click this key icon. After we connect to the Arduino or the link bot, although we don't have any link bot here in Taiwan, if we have Arduino board, then we can connect the Arduino board to the computer, and then update its firmware. After that, we may use these functions to control the Arduino and sensors, actuators directly with this website. So if you are familiar with the Arduino, I believe we need to burn some firmware inside the Arduino before we use Arduino to control hardware, right? But with this website, well, we can just drag some block functions and control sensors and actuators with Arduino directly. It's very simple. So that's why we use this website to teach young students math, robots, and programming. Another thing I would like to mention is we can still use this platform to control hardware link bot. Now it's virtual link bot. We can also only see the virtual link bot running on this figure. But when we switch to the hardware, all functions here, we can control the joints on the link bot. For example, we can set up the joint speed. Let me go back to the slides. We know that there are 2 motors on this link bot from both sides. So with this joint speed, set joint speed, we can control or set up the speed of each joint. And then we may control it to drive within the certain degrees, such as 360 degrees, then you will rotate 1 round. And so on and so forth. So actually, we can control the hardware link bot or Arduino with this website. Well, if you are not familiar with Arduino, well, probably this is a good platform to learn how to write programs. Because as I mentioned, we may set up the pin mode, let's say digital write, and then we can see the C program. This is what we can burn inside the Arduino and then make it work. Questions? Good. Okay. So, all right, since nope, let's me move on to the Omnibot. Where is it? Oh, by the way, let me show you this size first. Well, we may see there are a lot of functions inside the Robot Bracket, that website, but behind it, these are all functions. But how do we write a program inside these functions? At first, we wanted to drive forward, right? But in this case, it's very simple. If we set out the speed for 2 motors are the same, and the directions are also the same, then it will drive forward. And if we wanted to drive backwards, well, just change the direction of these 2 motors. Then it's supposed to drive backwards directly, right? Straight. And about turn right and turn left, well, based on your background, I believe your view will understand easily. If we change to use the positive direction with the rotor 1 and with the negative direction or opposite direction with rotor 2, well, you will turn right. Oppositely, you will turn left. Yeah, I believe this is very simple for you guys. But how about if we wanted to turn right like a car, like a vehicle? Well, we obviously the speed for motor 1 should larger than the motor 2. So you will drive forward and turn right. And so on and so forth. So if we may control the speed for each joint with the robot broccoli, then we may control the hardware link bot and to control this motion as we want, to make it drive forward, turn left, or drive backwards, something like that. Okay. All right. So let's see the Omnibot. Okay. Here. Let me set up the default coordinates. Delete the linkbot because we want to use the Omnibot here. Remove. Okay, this is Omnibot. Well, of course, it's a simulation here, but this is an Omnibot function. And you can find out several Omnibot functions. Oh, let me switch to this one. We can still see many Omnibot functions here to control this Omnibot, one Omnibot. With a very similar idea, if we actually to drive forward, well, we can set out the drive distance, 5 inches, and then click run. It will drive 5 inches. And of course, turn right, turn left. The key point will be this one. Directly drive the distance and angle. So if we actually to drive 5 distance at 45 degrees, you will drive to over there. Then we may learn its coordinates. Where is it? Here. It's its current position. So this is how young students or middle school students to learn math. If we can just use one function, I believe we may call its current. Probably not here. Okay, but at least we may see its current location here. Oh, it's raining now. Heavy raining. And we can still use some other functions. Set out the speed. 3. Let me copy another functions here. Negative 45 degrees. So where will it be? Well, we might have to do a very simple math equation to calculate the final location. But here, after we run this program, it will tell me its location will be at around 7 and 0 inch. Well, we can use the math equation to calculate its final location. But here, it's very simple to tell you the answer. Questions? I believe this is very simple to control single robots. Single robots, just with these functions. And of course, we can see the C programs here. This platform is totally free. You don't need to log in to use it. And if you are not familiar with C programs, probably this is a better choice for it to learn C programming with block functions. And then we can see how it works in C. Good. Okay. All right. Behind it, as we discussed before, we just simply use some functions to control Omnibot. and ask it to drive to the location we want directly. But what's the math behind it? This is its equations. If we know its velocity and the rotation speed, then we can calculate the rotation speed we need to control for these 4 wheels. And it's also true if we set up the speed or rotation speed for the 4 wheels, we may calculate its speed. So by this case, we may control it to drive to the specific location we want with these equations. This is a math behind this Omnibot. So besides we understand how we write some programs, of course, first we need to understand its mechanism or the math equations behind it. So we can write programs to control them. Good. Okay, so with this simple examples, it's around 3 o'clock. Probably we can take a break take a 10-minute break, and then you may play around how to control single robot. Right now it's only single robot. You may control single robot with Robot Bracket, this website. And later on, I will show you how we control multiple robots with this website, and show you some systems, multi-robot systems later on in the next hour. I think we may take a break, take 10-minute break, and we will go back at 3:10. All right, it's 3:10, so I think I should start. All right, in my slides, these 2 slides, I would like to show you how we control 2 link bots or 2 morning bots with Robot Bracket, and give you some background knowledge about how we control them. Okay, this is a very simple program I wrote before a few days ago to control these 2 link bots together. And then let me just run this program first. Well, as we can see that they drive at the same time. This is a key point, at the same time. It's not drive separately. So how we make it possible? Any ideas how we control these 2 robots at the same time? With only 1 program, as you see. There's kind of a long program here, but at least it's still a 1 program, not 2 programs or 3 programs. Thundering. All right. So you may probably notice that I think I can. Oh, I remember I can enlarge the code. Okay. Probably you may notice that we add some other functions called MB, drive distance MB, or turn left, turn right MB. NB means non-blocking functions, which means when you run these functions, you will kind of skip it and then run the next function directly. Okay. So, but behind it, it seems like that we skip this function first and run the next line. But behind it, actually is run this function behind in the background. So actually we have 2 programs in the background, although we are not able to see them actually, but it's true that this function is running in the background, and then the turn left function running in this website. So that's why we can control these 2. Let me run it step by step probably. We set out the speed, and it drives. And it drives. This will be like run this function first and run the next function later. But behind it, as I mentioned, you see it jumps the MB functions to run the next line first. But behind it, as I mentioned, we run these non-blocking functions in the background. So actually we have two programs. Let me show you another example. I'm not sure if it works. Let's see. Let me load my codes here. I remember it's 2. Load the code 4. Replace it. Replace. Okay. I hope it works. All right. There are 2 omnibots right now. Remove. There are 2 omnibots right now on this treasure island, and we wanted to drive it along with these edges at the same time. So here I use the for loop to make it possible. And with the same idea, here we may see the non-blocking function, direct distance angle MB, which means this is a non-blocking function. So we will run this function in the background, although we are not able to see it here. So when we try to control multiple robots, well, probably we need another program to control another robot and use one program to control the second robot at the same time. So if we have 3 robots, it's obvious we need 3 programs, one control each robot. So here, let me go back to my slides. In the robotics, we just use one program to control multiple robots, right? I just showed you. So here, we may code it as a centralized multi-robot system. The reason is we only have one computer, one program to control 2 robots. Well, in this figure, we may control like 5 robots, but in the robotics, well, we can also control 4 or 5 robots with that website. If we write the program in C, well, definitely we may control several robots, not only 5, probably 10 robots with one computer. As long as we have 10 programs, as long as we write 10 programs to control each one. But of course, in this case, as we know, if the central controller is dead, let's say our computer is done, it's broken, well, we are not able to control them anymore. So in this case, someone or scholars, researchers develop a decentralized system. In this case, there's no central controller, which means everyone can make this own decision with their computers. So each one have computers, controllers, actuators, sensors, or cameras, something like that. Everyone is a robot, and then they can communicate with each other. So even though some robots are dead, well, others may still work. So we can make this system much stronger or robust. In your case, well, we are talking about soft robots, right? Well, there are many soft robots on the table. If they are different, we call it a heterogeneous multi-robot system. And if they are all the same with this tiny worm robot, well, we call it a homogeneous multi-robot system. This is just a classification about the MRS. So in order to avoid this situation, the centralized MRS, because we know if the central controller is dead, we are unable to control other robots. So usually we use decentralized MRS or distributed multi-robot systems. So how do we control this robot? Well, we always want to learn how we control each robot in the group. So let's recall how we control one single robot. We know that there are some sensors, actuators, controllers, and computers, right, to create one single robot. So, by the way, I designed this for my PhD degree. At least we need hardware control agents. Well, you can assume that they are programs. we may need several programs to control each device, no matter actuators or sensors or cameras. And then we need to gather this information and understand the surrounding. So in this case, we need perception agents or some programs, at least to collect this information and analyze the surrounding. And finally, in the computer, inside the computer, we need planning programs to make decisions, such as there's a obstacle behind in front of me. I'm not supposed not to bump into it, right? So in this case, we need to write a program for planning, such as I need to turn around it or turn left or stop in order to avoid bumping into an obstacle. It's only for single robots, yes, for a single robot. But now we are going to control multiple robots, not just one. So in this case, we need some programs to exchange information, such as their locations, their tasks, or the maps. So we need several programs to exchange the information so that they can analyze the surrounding with the perception agents. And also, we need some coordination programs. Well, we know that robots are not able to bump into each other. They're supposed to avoid, right? Avoid collision. So in this case, we need some coordination agents to avoid this situation. And then also they may work together to complete the task, such as move one huge desk from one place to another place. So this is how we control multiple robots in a team with many programs, not just one, with many programs. And all of them are running at the same time. So that's how we control multiple robots. In my research, I focus on multi-robot task allocation. It means we have to assign tasks to robots to achieve a global goal and meet the requirements or constraints. Well, it's a very complicated problem. So that's why I think probably we're supposed to use some machine learning methods or AI methods to solve this problem. Well, I just list 5 machine learning methods. There are a lot of machine learning methods, but here I only list 5 of them. And then we want to choose one of them to solve this problem. Well, at the end, I choose Bayesian networks to solve this problem. The reason is usually we want to design a decentralized system instead of centralized system. And robots may have different skills, like crawling skills or gripping skills for the softer robots. They may have different skills if we put all robots together as a group. So usually the multi-robot system is heterogeneous. And definitely they are moving, just like crawling like this worm robot. So usually the environment is dynamic instead of static. So in the end, I chose to use the Bayesian networks to make the final decision to solve the MRTA problem. The idea is very simple. I want to find out the success rate for each test. If the success rate is higher, this robot is supposed to do that task, right? If the success rate is lower, this robot might not able to do this task. So other robots may handle that task. So here, my algorithm will be to find out the maximum sum of the success rate. So all robots may take their task and complete the whole mission within the maximum task success rate. Well, this is an algorithm to calculate the success rate, but I believe it's too complicated for you, so I would like to skip it. Basically, it says probabilities. These are conditional probabilities. All right, in order to test my algorithm, well, I test it in search and rescue mission. For example, this is a map of this rescue mission, search and rescue mission. we have 3 possible target points. So some robots, at least the 3 robots, supposed to go to this target point to detect the object, and then ask some other robots to move these targets out of this house or rack, just in order to save people. So we designed this task table. There are 7 tasks here. They all have meanings. Like we use task 1, task 3, task 5 to locate these targets, and then task 2, task 4, and task 6 to ask robots to move these targets from this building. This is robots I created for this experiment. As we can see that this is LinkBot, the very tiny education robot, and we add Raspberry Pi, a computer, the Arduino, a controller, and sensor. This is an IR sensor to detect the distance, and camera used to detect the object and recognize that, oh, this is a target. And we have another robot with a fixed arm and also with an IR sensor. So we can use these computers to communicate with each other in a decentralized system. So of course, they have different skills, right? One has a camera, one doesn't. So this is a heterogeneous multi-robot system. Okay, this is a video that to show you how we complete this search and rescue mission. These robots have camera, so they will go to the target points to detect the object. For example, this is going to detect this object. This one is going to here, and that one is there. After they detect the object or the targets, well, some other robots will try to move these targets to the safe places. Well, this is running under decentralized system, so there's no centralized controller here. Each robot can make their own decision. With the communication method I created, I just mentioned before about the algorithm related to task allocation. So in the end, well, luckily they complete the search and rescue mission and save people. All right. Then, well, I try to force some robots fail. Well, it happens sometimes, right? Just like the videos we just watched in the first class, they fail a lot. So what if some robots fail? What will happen? Well, other robots may take over its previous job and then complete the detection here at a target point, and then go to another target point to detect the target. And then, of course, with the same idea, some other robots may move the target to the safe places. And then mission complete. So in this decentralized system, we may see that even though here we only make one robot dead, well, this system may still complete this mission. Okay. Let's see the last one. Well, I add one non-obstacle here inside this environment. Well, we know in order to create a robot, we have some sensors or cameras, right? So they're supposed to recognize some unknown obstacles or unknown objects in the environment with sensors or cameras. So in this case, well, even though it detects the unknown obstacle, well, it will skip the task, and then other robots may take over the task and then detect the target points, and so on and so forth, as we know. So in order to create a robust multi-robot system, usually these are supposed to be decentralized and heterogeneous, and they're supposed to make their own decisions with some sensors, cameras, and of course the actuators in order to complete this mission. Okay, any questions? It's almost the end of my speech, but any questions? Okay. Let's watch other videos to make you have some other ideas for your project with software robots.
AMR and AGV robots are used across many warehouses and distribution centers today. Robotic automation improves employees' productivity, speeds up order fulfillment, and drives customer satisfaction. AGV robots have been around since the 1960s. AMRs have become popular in the last decade. So what's the difference between these two robotic systems? Automated guided vehicles, AGVs, are unmanned load carriers directed by software and sensor-based guidance systems. AGVs follow a pre-established path using permanently fixed magnetic strips and LiDAR for guidance. In that sense, an AGV is more like a train than a car. If something blocks its path, the robot will stop and call for help. They are mainly used to transport larger and heavier payloads and are best suited for environments that don't change often. Unlike AGVs, autonomous mobile robots, AMRs, can choose different routes to travel to their destination. AMRs are more flexible, which makes them more suitable for dynamic environments where requests are constantly changing. One example of AMR is in Via Picker robots. These robots use machine vision with fiducial markers. They can detect the position and orientation of fiducials with ultra precision. By sticking these markers on warehouse shelves, robots can easily localize themselves. Their sensors enable AMR to detect obstacles and automatically navigate around them. Software remapping can change the path of the robot without a need for extensive changes to the infrastructure. Because of that flexibility, AMRs are widely used in e-commerce fulfillment, where new orders are coming in all the time. So which one is better for your warehouse or distribution center? Although AGVs and AMRs can both be used to transport goods within your facility, they have quite different warehouse applications. The AGVs are most often used for larger, heavier payloads that need to be moved along the same defined path. AMRs are much more flexible and intelligent in the way they navigate the warehouse. They are optimally used for order picking, replenishment, and transporting boxes rather than large objects.
Okay, so based on the knowledge from this video, what's the robots I created for my research? Is it ABG or MR? Which one is this? Based on the information from this video. I believe it's MR, right, instead of AGV, because all robots can make their own decisions. They may walk around the obstacles on their own. There's no centralized system in my research, and there's no predefined path. They won't call, I remember they won't call help when it meets the obstacle in front of it. They can make their decision and pass around, go pass around the obstacle. So here, well, this is inside the factory or inside the warehouse. Based on this video here, this is a centralized system or decentralized system. What do you think? Based on this figure, probably this is centralized system because there's a very powerful computer to control each robot and actually to drive from one location to another location. And although it can still they can still create their path. But I believe this is a centralized system to allocate tasks for these robots. So as I mentioned previously, well, it seems a centralized system is not very good. Actually, if the central controller is dead, well, the whole warehouse cannot work anymore. So my future work will be how about if we create a decentralized system for it? Each robot can make their own decision. They may communicate with each other when they are nearby, and then they can avoid each other, avoid the collision. Then the system will be much more stable. So this will be my future work in the following years. Okay, let's see another video. Oh, by the way, I demonstrated my method with a search and rescue mission, but now this one is inside the warehouse. So there are a lot of applications actually. This is what I also want to do to demonstrate my method can work in other applications.
What mountain herd has 6 wheels and is bringing a fresh burrito to your door? A food delivery robot, of course. Inside this Starship bot is a meal ordered through DoorDash. It's coming soon to a sidewalk near you, as long as that sidewalk's in Redwood City, California. When you place an order, the robot springs to life and navigates to the restaurant. An employee puts the food inside and closes the hatch, sending it on its way. At the other end, you get a text message with a link saying your order's being delivered, and when the robot arrives, you unlock the hatch with a button on screen. Each Starship bot has 9 cameras and ultrasonic sensors for obstacle detection. They can travel as fast as 10 miles an hour, but are limited to 4 miles an hour for now. There's even a special mode that lets the robot cross the road safely. Human handlers will keep an eye on the bots during deliveries in this pilot phase, but the idea is they'll be almost fully autonomous in the future. I followed the bot around on a delivery run, and passers-by thought it was pretty cute. But what if someone tries to steal your meal? The robots only weigh 40 pounds, so if you're really hungry or strong, you could try and swipe it from the curb.
What we've built in are kind of variety of anti-theft protections. For example, we have cameras that keep us tracking two-way audio alarms. So if there's any tampering with the robot, theft attempts, the robot will immediately notify a human operator who can control the robot, speak to the vendor, or request police assistance.
DoorDash says it's using robots on shorter routes that their delivery humans, called dashers, tend to avoid. To our robot food delivery overlords, I salute you, and I'll have a pizza. Thanks.
Okay. Well, as we heard that this robot has, oh, right over here. It has some cameras and ultrasonic sensors, and it can drive, of course, as we can see. So definitely it's a robot. There's a computer or controller inside this robot. And what should we do in this case? Well, this is a product, commercial products in the US, of course. Well, what can we do to solve some problems? Can we see any issues here? Well, there we only show one robot here, right, to deliver our food. But how about if we have 10 robots like this, or 10 orders? Well, probably 10 is too small, probably 100. We have 20 robots and 100 orders. How should we solve this problem? How do we allocate these orders to these 20 robots? In the public area, like you can see, they are driving on the road, and there are many obstacles, no matter the pedestrians, cars, or probably pets. They have to avoid these obstacles on their own because we are not able to use a centralized controller to control them, especially when we have 20 robots. So our future goal will be how we coordinate them if we have a large number of tasks, or here in this case, orders, and also robots. This is what we want to solve this research problem in the future. All right, I would like to show you the last one, probably related to soft robots.
Introducing the mobile manipulator solution from Omron. Designed for safe collaborative work between humans and robots in manufacturing, the mobile manipulator combines Omron's autonomous mobile robot with an Omron GM collaborative arm. With the Omron GM collaborative built-in vision system, and landmark navigation, the mobile manipulator is capable of precise inspection, pick and place, sorting, and assembly. Coupled with a mobile robot that maps out optimal routes, detects obstacles, and safely reroutes around them, this solution unleashes the potential of automating new applications in a wide variety of industries. For pick and place operations, the mobile manipulator adds better traceability for high-value and delicate goods. For packing, the mobile manipulator can be used for palletizing applications, saving time in material transport and sparing people the tasks of heavy, repetitive lifting. Working by itself or integrated into a larger fleet of robots, the mobile manipulator is able to handle complex tasks, including pick and place, assembly, packaging, machine tending, inventory tracking, and transportation, unlocking the true potential of industrial robots. The mobile manipulator solution from Omron. What will you use it for?
Well, they are all commercial products here, according to this video. And they can drive around inside the factory. They all have some robotic arms on the top to grab something or pick up the package and transfer from one place to another place. And can anyone think of any research topics we can do according to this video? Well, in my research, I would like to develop some coordination related to between robots in the multi-robot system. Well, according to this video, we may probably see that each robot can only work individually, right? They are not able to work together. So what if this package on the top right corner, what if this package is very, very huge and heavy? Probably we need two robots to work together to move one package from here to another place. So how do we do that? Well, this is one possible research topic in my lab. And for you, because we are related to the soft robots, right? Well, as we can see, probably cannot crawl very well. So how about if we use many soft robots to solve this problem, to make it crawl inside the pipe? Probably it's possible, right? If we use several Arduino boards and use many soft robots and ask them to work together with individual programs, probably they can crawl through the pipe and successfully, right? Probably, right? So probably this can be your project in this course to make it possible by using many software robots and ask them to working together. Here also, where is it? Okay, as you can see that there are some grippers on these robotic arms. We may also use the software robots on them, as Professor Lin shows you. We may use this mechanism or software robots to grab some soft objects inside the factory. These are all possible research topics in the future. If you are really interested in robotics, well, probably this will be your research topic. Oh, yeah, still have 10 or 10 minutes. All right, any questions? Since I still have time, let me explain this a little bit for you. Well, this is someone's master's degree project, I think. I just found it on the YouTube. Hold on. On the top right corner, this is called the ROS system. We can use it as I believe I described this before. Usually we use a ROS system to control multiple robots because we can see the whole map here and we can see the result directly. And also we can control many robots and communicate each robot with the ROS system. Here in this project, we use a drone to fly around the environment to check the target points, obstacles, anything else? Probably not. Okay. And then after this drone complete to survey or explore this environment, then it assign tasks to these robots to go to the 5 targets sequentially. So actually, in this case, it's a heterogeneous multi-robot system, of course, because we have a drone, we have a multiple ground vehicles. In my research, well, I also want to create a heterogeneous multi-robot system. So we can do some research like this. Well, this is a very simple research problem. It just asks one drone to explore the environment and send text to robots. But what if we have many drones and many ground vehicles? How do we assign these tasks to drones and robots? Well, this will be a big deal. So that's how I will try to solve this problem. And also inside this video, they just use ROS as a central controller to send the tasks to drones and vehicles. So as I mentioned several times, we want to create a stable system, multi-robot system. So we're supposed to use decentralized system instead of a centralized system. So that's why we supposed to make this system robust with a decentralized system and with more drones and vehicles. Okay, questions so far? I guess I have to call Professor Lin back.
Excuse me, sir. I have a question.
Oh, okay.
Okay, can so like you said ROS system before. What does ROS stand?
Oh, okay. At the beginning, almost the beginning of my talk. Here.
I see.
Yeah,
okay,
we need the middleware to control all devices like cameras, sensors, controller, even controller, DC motors, and other actuators like LED or speakers. We need to use a certain middleware or software to communicate between them. So it's very common to use ROS. There are some other software architectures. I used Mobile C in my previous step in the US. Well, it's a very old software architecture, but now most people use ROS, Robot Operating System. So inside the video, here on the top right corner, this is the result when we run the ROS. We can explore the map and locate the obstacles and the target points with ROS.
Thank you very much.
Okay. Other questions?
I have a second question on the warehouse. So you said that instead of we have a like centralized system to control all the vehicles, we should, for the future work, we should like have decentralized system, right? Where the vehicles communicate to each other. But like, will it increasing like the number of communication made between the vehicles in real time? Like,
oh, okay. Yeah. All right. I think your question will be how we real time control them, right?
Yeah, like because like if you have a centralized system, like it will control all of them like at the same time simultaneously. But like if each vehicle has like own local, let's say like controller, I think it will be a lot of communication and like computation between like
yes. Yes, you're right, actually. Well, it's not easy to create a real-time controller with the decentralized system. And the communication is very critical, actually, in the decentralized system. So actually, there are pros and cons for centralized and decentralized system. Well, it's very easy to create this system with a centralized system because we may collect all data or all information from these robots or in the map. But in the decentralized system, they need to exchange their information when they're nearby or via Wi-Fi or the high-speed internet to exchange. Probably there's a robot on the top. Let me use a computer. Probably here's a robot there, and there's a one robot there. How do they communicate with each other? It's quite far away.
Yes.
So if we have enough routers, they may communicate with each other via Wi-Fi. So and if the bandwidth is wide enough, well, if the communication is good enough, well, they may communicate with each other. If not, as I mentioned in the decentralized system, they can communicate with a nearby robot and then go to another robot and go to another robot and finally communicate to the robot it want to communicate. So actually in the decentralized system, well, they can still gather enough information from other robots.
So like you divide and conquer between you divide into several regions and then you control
yes.
over.
Yes, because each
local
robot can exchange information. Yes, so that's why this is a difficulty in the decentralized system, and we want to solve this problem to create a stable decentralized multi-robot system. This is a very huge research topic and difficult, challenging research topic in the decentralized system.
But like because the decentralized system does have the benefits, like for example, when the central system broken, like some part of it can still function normally, right? Is that the benefits of decentralized system?
Yes, you're right. So that's why we need to, well, this video also describes some pros and cons. Which one? Probably this one. It also describes some pros and cons. When the size is huge, probably we need to use a decentralized system. But if the warehouse is small enough, well, probably we can just use a centralized system.
Okay. I think it should be the reverse. Like when the scale is really big, for let's say like 50 vehicles or 100, there will be a lot of communication between the vehicles.
Yes, you're right. Yes. Yes.
That
but
will increase the complexity. Yeah.
Yeah. So that's why the communication technique will be very complex in the decentralized system, especially when the group is large. So I believe some researchers also try to solve this problem with certain algorithms.
With a decentralized
if you are really
model.
interested, well, you can use Google Scholar and find out some research papers and then try to see how they solve this problem. You just ask.
Okay, thank you very much.
Okay. All right. So, at the end, Professor Lin may have some homework. There's it? Oh, here. Inside the professor's website, right? Lab website, and scroll down. Oh, my slides are here, a PPT and a PDF file. And we have a very tiny homework for you guys. Do I have to download it or not? Oh, I can obey it. Okay, good. Oh, we just asked you to find some research papers related to soft robots and give a summarize or your reading, your thoughts, personal thoughts after reading the research paper, and then submit to the Google form. When's the due date? On Sunday or Monday? On Sunday. On Sunday. Okay. And it's the same idea for my homework. Well, since this topic is related to soft robots, but my research topic is related to multi-robot system. So I hope you may find out some research papers related to many soft robots and try to see how they control them. Well, I tried to find out some videos related to many soft robots, but I cannot find one. Probably you can find one in your free time about the videos or the research papers. But here, since this is a homework, so I ask you to find one research paper to related to how researchers to control the soft robots. Hope many soft robots. Google Scholar. Okay, okay.
So maybe you don't have enough experience about finding a research paper. Actually, on Google search, there's something called Google Scholar. It's very easy to find research paper if you use Google Scholar. And for example, the topic assigned by Professor Zhuang, embedded soft robot. So just 3 keywords. Then you will see soft robot, embedded sensor, or maybe something like this. Embedded worm-like soft robot. Or if you want to say Arduino, not embedded. Arduino. Okay, then you can see, okay, some kind of soft robot gripping mechanism and using Arduino. There's something about Arduino inside the article. And usually most papers provides PDF already. In the past, it's not easy to get articles. Nowadays, it's very easy, okay? I recommend you take this paper as an example, just random paper. If you have no idea what to do, I recommend you first take a look at what this paper is about. Quickly glance through this paper. Okay, you can see, okay, some review of a soft gripper, some gripper. Okay, then it seems like it's making something experimentally. And okay, he made something very similar to what we mentioned in the class, right? Maybe different material. And he has some procedure for, I don't know what, collecting data, okay? And then, okay, here's the electronics for some research this person is doing, okay? Some data analysis, right? So when you quickly go through the paper, look at the figures and tables, you kind of can guess what this paper is about. Next, you can read the abstract, because usually the abstract is the most important part that help the reader to understand what this paper is about. If you find a paper and read the abstract and cannot understand this paper, change to a different paper. That means this author didn't pay enough attention to write the abstract. There are thousands of papers on internet. You don't really need to read this one, right? Just find the one you can easily understand. And maybe if you have issues about writing English, maybe you can learn something from the abstract. And if you want to study more, once you study the abstract, usually the abstract doesn't tell you the result. Abstract usually tell you what the story is about, what is the problem, what was done, and what do they expect to achieve. Usually they don't say too much about the result. If you want to read more, then you can go to the conclusion. There's usually a session about conclusion. Here, conclusion. So reading the first paragraph and the last paragraph sometimes help you to understand more. After simple reading, then you can make a decision of whether you choose this as the paper or not. Okay, so that's my suggestion. If you still don't know what to do, in my presentation file, actually, I told you there are some references at the bottom. You can just choose what I show you in the presentation. Okay, take which one? Like take this one as an example. Okay, if you enjoy this kind of research, see, I provide you the information at the bottom. Information in the bottom. So how do you get that PDF? You can just copy some portion of this article. Just copy, and then go to Google Scholar again. Google Scholar. Okay, go to Google Scholar. Right here, just paste what you got from the reference. You can tell it directly link you to the article, and you will see the PDF is provided. Just download and then take a look. This person, GM Whiteside, is a master from Harvard University. So he is the person I follow for so many years, since when I was a master student. So I know this person for 20 years, more than 20 years. So, but he's a master, so he likes to write. He doesn't put a lot of figures. So let me show you where the figures are from. Okay, here's one. Yeah, I took this figure from his article. If you are interested in this part, then you can read the paragraph related to that figure. Okay, and it's right now the reference papers are so easy to find. I don't think you will have difficulty finding the paper. I think the issue is once you have a paper, you may not understand how to write the 500-word report. Let me show you how short a 500-word report could be. Let me just take this one. Let me just copy his abstract. Okay, this is the abstract of that particular article. I just want to count how many words there is. Okay. Let me see. So this is 171. So maybe 300 words will be enough. Yeah, I mean the maximum is 500. Maximum. Okay, so you can write as short as this one, or even shorter. Okay. We don't want to give you a lot of pressure because only a few days. Just write something about what you learned. Okay. No huge pressure about this. And since we have so many lectures and maybe every professor will give you a little homework. So we may have a lot of homework. Every homework could be only 1 point. So we could easily give you a good score for that homework. You don't need to write a long one. The purpose of this homework is not to test how good your paper writing is. The purpose is for you to find something that is related to the project and just say something about what you found. Okay. Any question? Any questions from the online?